Okay, so we're on track. So today is Tuesday, October 13th, right? We have to remind ourselves of the day sometimes. Day 17. So I'm organizing the YouTube videos by day number. So today's day 17, right? Okay, so we're going to finish the right triangle Sohcahtoa trig 4.2 through 4.4. So trig values and trig identities. And then we're going to start talking about graphing sine and cosine functions. And I'm going to use what has been called the frame method by Tom Teagarden, my colleague, and by the author Carl Smith. So it's a different way of graphing trig functions that you might find better, actually. I find that trig books aren't very good at that. Okay, so we're going to continue chapter 4 today. Now, the chapter 4 homework overall. Chapter 4. So it's a short homework assignment. So try to do very well on it. It's a short homework assignment. Let me redraw this. Chapter 4. All right. The 4244, I'm going to come back to the last part of that near the end. All right. But the chapter 4 homework will be due on Wednesday, October 28th. So that's the week of Halloween. Try to stay safe that week. But the week of Halloween, Wednesday, October 28th, that's when the homework for chapter 4 is due. All right. Now the withdrawal deadline is the Friday before that. The withdrawal deadline is Friday, October 23rd. Okay. And I'm downloading and processing your previous homeworks. I might actually do your chapter 1 first because that may be more reflective of your ultimate grade. But I am in the process of downloading your homework. So you might get an email from me asking for access. If you gave me like a link to some file that required access, that link may have expired. So that's come up once or twice. So keep checking your email, and I may need access to some of those files. But I'm in the process of downloading and processing your prior homeworks. Again, I might do chapter 1 first, actually. And I do plan on having your first results by the weekend, by the end of the week, Saturday, Sunday, I'm hoping. And then the withdrawal deadline is Friday of, Friday of next week, October 23rd. Okay, but I got to get something in by then. All right, any questions about the schedule before we go on? We're doing chapter 4. Remember, chapter 4 is its own homework assignment that's due about a week and a half from now. All right, 2 weeks from Wednesday. All right, so any questions? Any questions? Feel free to put questions in chat. All right. Okay, we have a very full day. Let's start.
That's not quite standard, but it sounds more professional.
Slow down, buddy. Whoever you are, slow down. All right, so let's start.
Hi, everyone. We are continuing our discussion of trig functions and their values for special angles. Before, we discussed the special angles from 0 degrees to 90 degrees, or from 0 to pi/2 radians. So, for example, let's take a look at 30 degrees here. This 30-degree angle. The terminal side of the standard 30-degree angle intersects the unit circle at this green point. The x-coordinate is the cosine of 30 degrees, √3/2. The sine is the y-coordinate. The sine of 30 degrees is 1/2, the y-coordinate. Remember, sine of 30 degrees is 1/2. That's a basic fact you should remember. So this piece of the unit circle gives you the cosine values and the sine values for these special angles from 0 degrees to 90 degrees. And it turns out that these principles extend to the other quadrants and to the other quadrantal angles. Here, we're looking at the special angles in quadrant 1 and the nearby quadrantal angles. But we're eventually going to be able to look at all special angles with nice reference angles, the brothers, for all these. Okay, now these cosine and sine values can be encoded in the table, which you should be able to write pretty quickly. And there are patterns that we discussed last time. Now, we're going to extend our knowledge to the other quadrants. And again, we're going to organize the non-quadrantal angles in terms of families, basically families of brothers. Brothers, or we could refer to them as co-reference angles. That's not quite standard, but it sounds more professional. Co-reference angles. I like to call them brothers. You can call them sisters or siblings. These are angles that have the same reference angle. So for example, these four angles here, and I'm going to talk more about radian measure because it turns out that radian measure is actually more convenient if you want to hop from quadrant to quadrant. We have here an acute angle, 30 degrees or pi/6 radians. This is an acute angle, and the reference angle for any acute angle is itself. The reference angle of 30 degrees or pi/6 is itself, 30 degrees or pi/6. And we know the cosine and sine for this special angle from the table or the unit circle. Now we can use that information to tell us about what's going on with its brothers. There are three other brothers for pi/6 between 0 and 2 pi. These are the most famous four brothers that have pi/6 as the reference angle. The ones between 0 and 2 pi. Actually, negative pi/6 is also pretty famous. That's also in quadrant 4. It's coterminal to 11 pi/6 over here. We're going to start with these special angles from 0 to 2 pi radians. And why are these brothers? Why are these co-reference angles? Because they share the same reference angle. A reference angle is an angle that a non-quadrantal angle, so we don't want like 90 degrees, it's the angle that a non-quadrantal angle, if you look at the terminal side, the angle that the terminal side makes with the x-axis. And it's always going to be acute. By definition, reference angles are always acute, like 30 degrees. So here, the 150-degree angle, or 5 pi/6 radians, that has the same reference angle, 30 degrees, or pi/6 radians. This acute angle is the common reference angle for all four of these angles, 5 angles if you include this over here. Again, over here, for 210 degrees, or 7 pi/6 radians, we have the same reference angle, the angle that the terminal side makes with the x-axis. Over here, for both 11 pi/6 and negative pi/6, we have the same reference angle, 30 degrees, or pi/6 radians, between the terminal side and the x-axis. Again, I refer to these angles, all 5 of these, as brothers or co-reference angles. You can think of this x here, connecting these various angles. An angle has infinitely many brothers in this sense, because remember, coterminal angles are like twins. So the brothers would include all angles coterminal to pi/6, 5 pi/6, 7 pi/6, and these guys. So every angle has infinitely many brothers, as long as it's not quadrantal, like 0 or pi/2. And why do we care about these brothers? Because it turns out that they're going to have the same cosine value, sine value, and so forth, the same basic trig values up to the sines. They may differ in terms of which values are positive and which values are negative. But in absolute value, they're going to have the same sine values, cosine values, tangent values, and so forth. By value, I could mean undefined. That could be the case for the quadrantal angles. Okay. Now, in addition to this pi/6 family, and here were computations that explained how to get to the other brothers, because there was a shortcut. And in fact, let's review the shortcut before we get to the other families. Again, what's a quick way of hopping from quadrant to quadrant and getting these brothers? The radian measure actually turns out to be more convenient, more so than the degree measure. Again, let's start with pi/6 radians. And remember that this trick will extend to these other 2 families we'll talk about later on, for pi/4 and for pi/3. So how do we get the brothers in the other quadrants? 5 pi/6. Remember, 5 is 1 less than 6. That's the famous brother in quadrant 2. 7 pi over 6. 7 is 1 more than 6. That's the famous brother in quadrant 3. 11 is 1 less than twice 6. 11 pi over 6, that's the famous positive brother in quadrant 4. Although often we like this coterminal angle, negative pi over 6. Those patterns extend to the families. These groups of brothers for not just pi over 6, but for pi over 4. Here are the famous positive brothers for pi over 4, and for pi over 3. These are the famous positive brothers for pi over 3. Of course, an angle is its own brother in that sense. Now, coterminal twins have the same trig values, including the sines. So, for example, 11 pi over 6 and negative pi over 6 will have the same sine values, cosine values, tangent values, and so forth, including the sines, positive and negative. Again, for brothers, we have the same values in absolute value, but the signs may differ. Okay, so let's use these ideas of brothers or coreference angles to look at angles outside of quadrant 1. So for example, before, we talked about the 30-degree angle, or pi over 6 radians. Let's say that we now care about the 210-degree angle, or 7 pi over 6 radians. We know everything about this angle over here, the reference angle. We knew this from the unit circle, or the table, but now we're going to figure out how the data for this angle will change or extend out to this angle over here in quadrant 3. Now, many people might prefer the unit circle approach, and we'll discuss that. But first, I'll talk about the right triangle approach, because many students get so used to right triangles. And you can use right triangles, but there's a twist. You have to be prepared to put negative numbers to represent signed side lengths if you have a side that's going down below the x-axis, or a side that's going to the left from the y-axis. Be prepared to put signed lengths like these over here. Because remember, 7 pi over 6 is a quadrant 3 angle. It's a bit more than pi radians. A bit more than pi radians. We rotate into quadrant 3, where both the x and y coordinates are negative. And from the unit circle approach, we know that the x-coordinate is the cosine value, the y-coordinate is the sine value. They're both going to be negative. In the right triangle approach, what would we do? Well, you might figure out this right triangle from back in quadrant 1 for the 30-degree angle. For this 30-degree angle, on the unit circle, we have a hypotenuse of 1 unit. The shortest side, which faces the small 30-degree angle, is half the hypotenuse. So this side length here is 1/2. And the medium side here is root 3 times as long as the shortest side. So this medium side facing the 60-degree angle will be root 3 over 2, which is root 3 times the shortest side, 1/2. Actually, and I'll use another color here, some people might actually prefer to use a circle of radius 2 here if you're dealing with a 30-degree or 60-degree angle. Because if the hypotenuse is 2 units, then the shortest side is 1 unit, and the medium side is root 3 units. And then it was easier to think about Sohcahtoa and figuring out sine, cosine, and tangent. But to make things more consistent, let's keep this as a unit circle, and I'll keep this hypotenuse as 1. So let's look at these red values here. 1/2, root 3 over 2, and 1. In purple, we see the same values in absolute value. The hypotenuse is always positive. We always label the hypotenuse with a positive number or length. This could be 1 meter, let's say. But take a look. On the red triangle, we had positive root 3 over 2 on this side. But for the purple triangle, we're going to put negative root 3 over 2 because this side is going to the left of the y-axis. Likewise, we're going to put negative 1/2 on this leg because this side is extending down from the x-axis. So now we can use Sohcahtoa relative to this reference angle. I know we're talking about 210 degrees here, but we really want to think in terms of this reference angle when we use Sohcahtoa. So for example, what is the sine of 210 degrees? The sine of 210 degrees. Right off the bat from the unit circle, we know that it's going to be -1/2, which is the y-coordinate of the intersection point. But even on this right triangle, sine, SOH, sine is opposite over hypotenuse. -1/2 over 1 is -1/2. So our reading from the right triangle is consistent with our reading based on the unit circle and this intersection point. This intersection point has coordinates -√3/2. I'm taking the unit circle approach now, comma, -1/2. Again, this is the cosine, this is the sine. And I'll tend to prefer the unit circle approach in my notes. But again, if you really like dealing with right triangles, then you can work in this fashion. And if you don't like fractions, you can take 2 as your hypotenuse. So we're going to take the unit circle approach for this in the next lesson.
All right. Any questions so far? So, okay. So I did hear the right triangle approach. Personally, I like the unit circle approach. Now, if you love right triangles, go for it. But I think the unit circle approach might be more elegant for you. So if this seems too busy, I don't blame you. I think so too, actually. Any questions? Any questions? Feel free to ask questions in chat. All right. Going on.
Hi, everyone. We're continuing our adventure through the other quadrants outside of quadrant 1 and trig values for special angles. Now before, we talked about the 30-degree angle here, or pi/6 radians. Its cosine was the x-coordinate of this intersection point, √3/2. The sine was the y-coordinate, 1/2. Notice these are both positive. X and y are both positive because we're in quadrant 1. Over here, 7pi/6 is in quadrant 3. Notice the x and y coordinates are both negative, and these values are the same as the values over here in red, except these are signed negative. A great thing about brothers is that they're going to have the same trig values, except maybe for the signs, positive versus negative. From pi/6 to 7pi/6, both these values flip from positive to negative. Actually, the tangent will be the same. The slope will be positive in both cases because slope is positive here in quadrants 1 and 3 for tangent. So let's talk more about this unit circle approach to trig, which perhaps may be more convenient than the right triangle approach. What's a quick way of finding the signs of the trig values, positive versus negative, in the various quadrants? And remember that reciprocal values have the same sign. So for example, if sine of theta is positive, then so is cosecant of theta. So if we understand the deal with sine, cosine, and tangent, we can know the deal with cosecant, secant, and cotangent. ASTC. This is an acronym for many phrases. All students take calculus. I know some ones that are not as polite, but all students take calculus. That's one way of remembering ASTC. This is a quick way of remembering which trig values are positive in the various quadrants. ASTC. A. All of the 6 basic trig functions, sine all the way through cotangent, are positive in quadrant 1. That makes sense because in quadrant 1, x and y are positive and all the ratios are positive. A for all. In quadrant 2, let's go to blue here. In quadrant 2, sine of theta is going to be positive, and also cosecant of theta. It's reciprocal. I should put the parentheses theta here, but I might be a little sloppy with that. All right. In quadrant 3, T for tangent. I'll put that in brown. Tangent and its reciprocal cotangent of theta will be positive in quadrant 3. Tangent of theta and its reciprocal cotangent of theta. And in quadrant 4, I'll put this in orange. In quadrant 4, cosine of theta and its reciprocal secant of theta will be positive. And the others would be negative. So when I say that, for example, in quadrant 2, sine and cosecant are positive, that means the other 4 are negative. In quadrant 3, these 2 are positive, the other 4 are negative. In quadrant 4, these 2 are positive, the other 4 are negative. All students take calculus, ASTC. You start in quadrant 1 and you go counterclockwise, as usual. Again, a quick way of knowing which trig values are positive versus negative in each quadrant. And this is a real breakthrough, because if you know the deal in quadrant 1, the piece of the unit circle in quadrant 1, you don't really have to draw the whole wheel, the whole circle, to figure out what's going on with the special angles, the brothers, in quadrants 2, 3, and 4. Let's apply these ideas. And actually, before that, let's explain why ASTC works. Let's do that first. Okay, so remember that if you have the unit circle, pretend that's a circle. All right. And if we consider a standard angle and an intersection point there, the coordinates of this intersection point will be given by, if theta is the standard angle here, if theta is the standard angle here, the coordinates of this intersection point are cosine of theta, the x-coordinate, comma, sine of theta, the y-coordinate. All right, so what's the deal with sine of theta? What's the deal with sine of theta? I'll circle that in red over here. What's the deal with sine of theta? Sine of theta is the y-coordinate. In what 2 quadrants is y, or sine of theta, positive? In quadrant 1 and also in quadrant 2. However, sine of theta is negative in quadrants 3 and 4 because the y-coordinate is negative in quadrant 3 and 4. You can imagine a unit circle like so. Pretend that's a circle. Now, what about cosine of theta? Cosine of theta, I'll put that in blue. Cosine of theta, or the x-coordinate on the unit circle. Where is the x-coordinate positive? In what 2 quadrants? X is positive in quadrant 1 again, and this time quadrant 4. Cosine is positive in quadrants 1 and 4, and it's negative in the other 2 quadrants. The quadrantal angles, you would focus on the coordinates. All right, now what about tangent of theta? Remember, tangent is slope. Tangent is slope. Also, you can think about sine over cosine. For example, we know that in quadrant 3, tangent will be positive because a negative divided by a negative is positive. But more simply, okay, again, here's the deal for tangent of theta. Tangent is slope. Tangent is slope. In what 2 quadrants will slope be positive if you consider lines through the origin? Well, in quadrant 1 and quadrant 3. And tangent is negative in the other 2 quadrants, 2 and 4. So again, to understand the sign, positive versus negative, of sine, cosine, and tangent, remember, sine is y, not x, cosine is x, and tangent is slope. And you can figure out the signs, positive and negative, very quickly. Again, the quadrantal angles, you'll have to look at particular coordinates. Okay, let's go ahead and do some examples now. Example. Let theta be 19 pi over 6. Find the 6 basic trig values for this special angle. We know it's a special angle because it's simplified, we have an integer, times pi over an integer, and this bottom integer is 3, 4, or 6, which means that we have a special angle that's not quadrantal. And it turns out we can find the reference angle very quickly in these cases. Basically, you look at the denominator. From the denominator alone, we can figure out that the reference angle is pi over 6. Bear in mind, that would not work if that were a 5 or a 7, for example. It turns out that that trick for reference angles works for the brothers, for pi over 3, pi over 4, and pi over 6. Okay. We have a problem. 19 pi over 6 is too big. It's not between 0 and 2 pi. By the way, I put a parenthesis there because 2 pi is itself coterminal with 0. But again, 19 pi over 6 is too big. It's bigger than 2 pi. So first off, we want to find a coterminal angle to 19 pi over 6 that does lie on this interval. Or it could be slightly negative, like negative pi over 6. If we get negative pi over 6, that could also work nicely. Well, how can we get a smaller angle? We can take this, and we can get a smaller coterminal angle by subtracting what? By subtracting 2 pi, which corresponds to a full revolution clockwise, in this case. And we're subtracting. Again, if we end up with a nice negative angle, that's okay too. But what happens here? We start with 19 pi over 6. We subtract 2 pi. So we're revolving, again, clockwise 2 pi. We're going in reverse. Now, when we subtract 2 pi, what are we subtracting? 2 pi is 12/6 pi, or 12 pi over 6. When you subtract 2 pi, you're subtracting 12 pi over 6. 19 pi over 6 minus 12 pi over 6 is 7 pi over 6. And 7 pi over 6, I'll put this in red, 7 pi over 6 is a great coterminal angle. It's a coterminal angle, which will be in the same quadrant as 19 pi over 6 and have the same reference angle. And he's going to be between 0 and 2 pi. Okay. And we like coterminal angles because the 7 pi over 6 will have the same trig values as 19 pi over 6, including the signs, positive and negative. So 19 pi over 6 and 7 pi over 6 will have the same data sheet in terms of the 6 basic trig values and also in terms of their reference angle and quadrant. Coterminal angles that aren't quadrantal have that great property. They have the same reference angle and quadrant. Again, the reference angle for 7 pi over 6 is pi over 6. Basically, look at the denominator. If you have a nice fraction like that, look at the denominator, pi over 6. And we recognize that 7 is 1 more than 6. What quadrant was that the trick for? It was the trick for quadrant 3. Basically, remember that pi radians corresponds to the negative x-axis, and we're rotating a bit more than that. Okay, pi is 6 pi over 6. 7 pi over 6 is a bit more. So we're in quadrant 3. So we know two key things. In fact, I'll type it out. What do we know about both of these? I'll type this out. For both angles, what do we know? The reference angle is pi over 6, and the quadrant is quadrant 3. If you know the reference angle and the quadrant, and the reference angle is a known special angle, hey, we're in business. We can find everything exactly. All right. What's the deal with pi over 6? We know all of its data from the table or from the unit circle, right? So you should remember that sine of pi over 6 or 30 degrees is 1/2. In fact, let's say we start from scratch, right? We have the unit circle, okay? Pi over 6 or 30 degrees, that's kind of flat. And the intersection point's over here. X-coordinate is cosine, y-coordinate is sine. This point is the talk radio point. It's low and to the right. It has a low sine value, 1/2. The sine of 30 degrees, or pi over 6, is 1/2. The cosine is the high value. It's √3/2. So we know the sine and the cosine. The tangent is the quotient of these. That over that is 1/√3, or rationalized, it's √3/3. Again, you can get this from your table. By the reciprocal identities, we can flip these fractions to get their reciprocals. What's the reciprocal of sine of theta? Careful, it's not secant of theta, it's cosecant of theta. So cosecant of pi over 6 is the reciprocal of 1/2, or 2. Secant of pi over 6 is the reciprocal of that. That's going to be 2/√3, but we want to rationalize. We multiply by √3/√3, or 1. This is 1. And the result is 2√3/3. Finally, for cotangent of pi over 6, we take the reciprocal of tangent of pi over 6. Actually, it's easier to flip that fraction. When you flip this fraction, you get √3. So you should be able to figure out, or get from your table, the 6 basic trig values for pi over 6, the reference angle. You should be able to figure these out very quickly. And guess what? To get the data sheet for either 7 pi over 6 or 19 pi over 6, they have the same data. You just have to worry about the quadrant. It's now quadrant 3. In fact, we're in quadrant 3. All right. So what's the deal here? What's the deal here? We're in quadrant 3. So which trig values are positive and which are negative in quadrant 3? Look over here, the t. That tells us that tangent of a quadrant 3 angle is positive, and also the cotangent, the reciprocal for that angle, will also be positive. These will both be positive, and the other 4 will be negative. So what do? We take the data sheet for pi over 6, the trig values for pi over 6, and we just have to attach the appropriate signs, positive or negative. So again, for either 7 pi over 6, which was the nice coterminal angle, or really the guy we cared about at the beginning, 19 pi over 6, that's the one we were really asking about, what do? We take the trig values for pi over 6 and just sign them appropriately. As you do your work, you don't even have to worry about writing this middle column out, over here and over here. Bottom line, what are the special values, the 6 basic trig values for 19 pi over 6? We get them from this column and from this column, snaking around. Again, these trig values are the exact same ones as for pi over 6 in absolute value, but we have to care about which ones are positive and which ones are negative. Again, in quadrant 3, all students take calculus. In quadrant 3, t, which stay positive? Tangent and cotangent. So the √3/3 stays positive for tangent. For cotangent, the √3 stays positive √3 for this angle. But the other 4 trig values go negative. Sine of 19 pi over 6, that's negative 1/2. Cosine of 19 pi over 6, that's negative √3/2. Again, tangent of 19 pi over 6, that stays positive, √3/3. The tangent of a quadrant 3 angle, whether this or this, is √3/3. Cosecant of 19 pi over 6 is negative 2. These are reciprocals again. Secant of 19 pi over 6 is negative 2 √3/3. Cotangent of 19 pi over 6 is √3, like before. Not just for 7 pi over 6, but for pi over 6, the original reference angle. So again, what was the great trick with the unit circle? Find the reference angle and the quadrant. Get the data sheet for the reference angle. You better know those quickly from the table or the unit circle. You better know pi over 6 and its data. Know what quadrant we're in with the new angles. 19 pi over 6 and its coterminal angle, 7 pi over 6. They were both in quadrant 3, which means that we take the data sheet for pi over 6, we keep the tangent and cotangent values positive, we flip the others to negative, and then we get the data sheet for both 7 pi over 6 and the guy we really cared about, 19 pi over 6. We're going to continue with more examples in the next video.
Okay, so using this kind of scheme, you should be able to find the 6 basic trig values for any special non-quadrantal angle. All right, so you're more powerful. Any questions? Any questions? So big review of trig, right? Any questions? Put questions in chat. Let's keep going.
Hi everyone, we're continuing our adventure of finding trig values all around the world. In this example, we'll evaluate, or simplify, basically, cosecant of 7 pi. Well, 7 pi is too big, so it will help to find a nicer coterminal angle. Let's find a nicer coterminal angle. Well, to find coterminal angles, we can add or subtract 2 pi. We start with 7 pi. If we subtract 2 pi, we get 5 pi. If we subtract 2 pi again, we get 3 pi. If we subtract 2 pi again, we get 1 pi. And 1 pi is finally a pretty nice angle. So let's go ahead and say that 7 pi is coterminal with pi. We know pi pretty well. Now, if this seemed too tedious for you, well, remember that when we go from 7 pi to pi, we're basically subtracting 6 pi. And that is legal. You can get a coterminal angle by subtracting 2 pi, 4 pi, 6 pi, or so forth, or add those angles. However, do not add or subtract 1 pi, 3 pi, or 5 pi, otherwise you'll be on the other side of the origin, and you don't want to do that. So to find a coterminal angle, you can add or subtract 2 pi, 4 pi, 6 pi, 8 pi, and so forth. Here, you can subtract 6 pi. All right, 7 pi is coterminal with pi, which means that cosecant of 7 pi will be equal to cosecant of pi, or maybe they're both undefined, in which case equals would technically not be appropriate. All right, so what's the deal? Cosecant of pi, well, I know sine better, right? Cosecant of pi is the reciprocal of sine of pi. Cosine of pi is the reciprocal of sine of pi. What is the sine of pi? I'll put this in blue. What is the sine of pi? The sine of pi is the y-coordinate of this point over here on the unit circle. What's the y-coordinate of this point corresponding to pi radians? The y-coordinate is, it's 0. So we're talking 1 over 0. 1 over 0 is undefined. Cosecant of pi is undefined, therefore this thing is undefined. Cosecant of 7 pi is undefined. That happens sometimes. For quadrantal angles, that can happen. By the way, cosecant of pi was also undefined. Okay. Now let's say you're dealing with degrees. Remember that finding reference angles for special angles is very easy if you're dealing with radians. For degrees, it's actually a bit trickier. So let's say that you have an angle, theta, that you care about. First.
By the way, one comment. I mentioned before, the reciprocal of sine of pi is cosecant of pi. I may have said cosine. The reciprocal of sine of pi is cosecant of pi. All right, just to clarify that. That correction was in my YouTube video.
Want to find a coterminal angle alpha, because your angle theta might be too big or too small or negative. So find a coterminal angle alpha that's either between 0 degrees and 360 degrees, or it could be slightly negative. So here's how you would find a reference angle for either theta or alpha, this nice coterminal angle. Bottom line, you're going to take the absolute value of some flat angle minus alpha, this nice coterminal angle you're dealing with. It could be the original angle. Now, what do I mean by a famous flat angle? Okay, so the flat angles basically correspond to the x-axis. 0 degrees over here, 180 degrees. Back over here, 360 degrees. Okay, these are the relevant flat angles. Okay, but in the vicinity of 0 degrees to 360 degrees. Determine which famous flat angle associated with the x-axis is closest to your angle alpha among these. Okay, and the reference angle is going to be the absolute value of the difference between the two. So absolute value of flat angle minus alpha. We'll apply this in just a moment. So for example, let's evaluate the tangent of negative 225 degrees. Right off the bat, you might want to convert negative 225 degrees to radians and use the procedures we've used before. That might be easier. But let's say that you want to stick with degrees. Well, there's a problem. Negative 225 degrees is a pretty bad negative angle. I'm sure we'll want a coterminal angle. And how can we find a coterminal angle for negative 225 degrees? We add how much? We add 360 degrees. When we do that, we observe that negative 225 degrees plus 360 degrees is 135 degrees. That's our value for alpha, the nice coterminal angle. And then, what's the reference angle for both these guys, the 135 degrees and the negative 225 degrees, right? Well, incidentally, you might care about the quadrant first. What quadrant is 135 degrees in? 135 degrees is going to be in quadrant 2. Quadrant 2. This is 135 degrees. All right, quadrant 2. We're in quadrant 2. All right. Now, what's going to be the reference angle? What's going to be the reference angle over here? The reference angle over here. We use this formula. The absolute value of the relevant flat angle minus our alpha, 135 degrees. What's the closest flat angle to 135 degrees? It's going to be 180 degrees. That's the closest one of these three to 135 degrees. So we take the absolute value of 180 degrees minus 135 degrees. That's 45 degrees. That's going to be the reference angle. So at this point, I know the key information for both this angle and this angle. I know that the reference angle, I'll type this out. I know that the reference angle is going to be 45 degrees, and I know that we're in quadrant 2. That's true for both the 225 degree angle and the 135 degree angle. Now we're down to 45 degrees. Bottom line. This thing here is either going to be plus or minus the tangent of 45 degrees. We're getting down to that reference angle in quadrant 1, a famous acute angle. What is the tangent of 45 degrees? What's the tangent of 45 degrees? It's 1. Famously, it's 1. So our answer is going to be either plus or minus 1. Plus or minus 1. But which one is it? Well, we're in quadrant 2, remember? We're in quadrant 2. And in quadrant 2, slope is negative. Slope is negative. Also, all students take calculus. In quadrant 2, sine and cosecant are positive. The other guys, like tangent, they're negative. So the tangent of negative 225 degrees is going to be the same as the tangent of 135 degrees because these two angles are coterminal. The answer for both will be negative 1. 1 is the tangent of 45 degrees, the reference angle, but we have to sign it negative because these two angles over here are in quadrant 2. That's a lot of stuff there. It might be easier to just go to radians. In the next video, we're going to talk about some more identities. we've dealt with 3 groups. We're going to deal with groups 4 and 5 next time.
Okay, so this finishes basically finding your basic trig values, and we're going to go to the more algebraic identity stuff next. Any questions before we go on? Any questions before we go to the identities and a bit of algebra? Any questions? All right, feel free to ask questions in chat. All right, let's go on.
Hi, everyone. We're going to introduce some more trig identities. Thus far, we have looked at 3 groups of trig identities. First, we looked at the reciprocal identities. For example, cosecant of x is the reciprocal of sine of x, and vice versa. It does go both ways. We have these other identities here. Remember that in basic trig, 0 and undefined are basically reciprocals of each other. In our second group, we had the quotient identities. Tangent of x is equal to sine of x over cosine of x, and cotangent of x is the reciprocal, cosine of x over sine of x. The third group we dealt with here, the cofunction identities, which are best summed up by this statement: cofunctions of complementary angles are equal. Cofunctions of complementary angles are equal. So for example, the sine of 30 degrees equals the cosine of 60 degrees. There are many, many cofunction identities. For example, if x is measured in radians, we could say that sine of x equals cosine of the complement. Also, vice versa, cosine here, sine here. Also, tangent and cotangent, cotangent and tangent, secant and cosecant, cosecant and secant. There are many, many cofunction identities. So beyond the reciprocal, quotient, and cofunction identities, there are 2 more groups of identities we'll discuss now. Next up, we have the even-odd or negative angle identities. The even-odd or negative angle identities. And this is related to the notion of even functions and odd functions back in chapter 1. In fact, we're going to identify which of the 6 basic trig functions are even and which are odd. None of them are neither. Each one is either even or odd. So to do this, well, remember that for even functions, right? If we wanted to know if f was an even function or an odd function or neither, we would take a rule for f of x and we would consider f of the opposite of x and analyze that and see if the result was equal to this, in which case we had an even function, the opposite of this, in which case we had an odd function, or we could have the neither case. And remember, the domain had to be symmetric about 0 to have an even or odd function. So similarly, we're going to consider an angle theta. Here, for the sake of convenience, let's assume that the angle theta is acute, or at least quadrant 1. And we're going to consider the opposite of theta, or negative theta, informally. All right. So question, is the sine function even, odd, or neither? The sine of theta is the y-coordinate of this blue point over here. The sine of opposite of theta, I'll move this up a bit. The sine of the opposite of theta is the y-coordinate of this brown point over here. Question, compare the y-coordinates of the blue point and the brown point. Are they going to be equal, opposite, or neither? In fact, imagine this angle theta decreasing or increasing. Think of an animation where this angle increases, the blue point rotates this way, this angle goes this way, this brown point goes this way. What's happening with the relationship between the y-coordinates? They're always going to be what? They're always going to be opposites. For example, here, the y-coordinate of this point is positive, the y-coordinate of this point is the opposite. It's going to be negative. But by symmetry, they are going to be opposites. They are going to be the same in absolute value. They're going to be opposites. So what can we say in general for the sine function? If you imagine this animation, the blue point going along like this, the brown point going along like this. We can say that for any angle theta, theta could even be 1,000,000 radians. For any angle theta, we can say that sine of opposite theta is the opposite of sine of theta for all real values of theta in radian measure. Just like when we considered the x cubed function, right? The x cubed function represented an odd function. And why is that? Because if we replace or substitute x with its opposite, basically the negative sign pops out and we get essentially negative x cubed. The negative sign pops out. Similarly, for sine of negative theta, this -1 factor pops out and we get negative sine of theta. That indicates that sine is an odd function. The sine function is odd. I'll type that out. Sine is odd. The sine function is an odd function. Basically, this negative sign pops out. Kind of like for the x cubed case over here. The cube of opposite x is the opposite of x cubed. Sine is odd. Now, what about cosine? I better do some erasing here. Okay, what about cosine? Remember, cosine corresponds to x coordinate. Cosine corresponds to the x coordinate. Compare the x coordinate of the blue point with the x coordinate of the brown point. We're comparing cosine of theta and cosine of opposite theta, or negative theta. Look at the x coordinates of these 2 points. Are they equal, opposite, or neither? And you can imagine the animation as well. The x coordinates will always be equal. The cosine for negative theta, or opposite theta, is going to be equal to the cosine of theta. And that's true for all real values of theta, all angles. For any angle theta, cosine of opposite theta is just cosine of theta. So in that sense, it's kind of like the x square function. The x square function is going to be even. And why was the x square function even? Because if you take the square of opposite x, you replace x with the opposite, the square of opposite x is plain old x squared for all real x. This equals this for all real x. So that means that the x square function is even. The negative sign basically dies. It gets killed by the square. Likewise, when you consider cosine of negative theta or opposite of theta, basically we can kill the negative sign and we're just left with cosine of theta. Just as if we take the square of opposite x, we can kill this negative sign, we get x squared. So this tells us that, like the x squared function, the cosine function is even. Cosine is even. The x coordinates for these 2 angles, these points, will be the same for any real value of theta, any angle. All right. Now, what about tangent? That's like a tiebreaker. Is tangent going to be even or odd? What is tangent? When we think of tangent, we think of what concept? In fact, I'm going to erase these circles here. When we think of tangent, we think of what concept? When we think of tangent, we think of slope. We're going to compare the slope of this red line segment, tangent of theta, with the slope of this brown line segment, tangent of opposite theta. Look at these 2 slopes. are they going to be equal, opposite, or neither? They're going to be opposite. For example, if this slope is positive 2, this slope here will be negative 2. And you can imagine the animations. Bear in mind, tangent of pi over 2 is undefined, tangent of negative pi over 2 is undefined. That sometimes happens. But basically, as long as we don't have a domain problem, these two values will be opposites. So tangent is like sine in that sense. As long as these are defined, okay? The tangent of opposite theta, what can we do? Just like for sine, we can pop out the negative sign. The tangent of opposite theta is equal to the opposite of tangent of theta. The negative sign pops out, like in the cubing case. Remember, the x cubed function was odd. The x cubed function is odd because when you substitute x with its opposite, you end up with the opposite. In this case, well, as long as we don't have a domain problem. This was true for all reals. The domain for tangent, as we'll see, will be symmetric about 0. That may not be obvious now. Well, you know, if you consider moving away from the 0 angle, you can kind of see it. The domain will be symmetric about 0. For example, we have problems at pi over 2 and negative pi over 2, and so forth. Anyway, tangent of opposite theta equals opposite tangent of theta. This negative sign pops out. As long as these are both defined, as long as we don't have a domain problem. Sometimes they're both undefined. So again, what are we concluding here? Of these three functions, sine and tangent are odd, and cosine is even. In other words, cosine, and by the way, its reciprocal function, secant, technically I should write these out. Cosine and its reciprocal function, secant, are even, right? Cosine and the reciprocal function, secant, are even. So for secant, this negative sign would also die. But the other four trig functions, sine, tangent, and their reciprocals, cosecant and cotangent, are all odd. Meaning, for example, cotangent of negative theta equals negative cotangent of theta. That negative sign would pop out. So those are the, over here, even odd or negative angle identities. Among the 6 basic trig functions, cosine and its reciprocal function secant are even. So if you're taking the cosine or secant of negative x, basically, the negative signs can die and you're left with these. Secant sometimes falls apart. The other 4 trig functions are all odd. So for sine, cosecant, tangent, and cotangent, if you're taking these for negative x or opposite of x, the negative sign pops out in all 4 of these cases, provided that these are defined. Bear in mind that these 3 trig functions here are sometimes undefined. And what does this mean graphically? Well, we're going to graph functions pretty soon. Remember that the graph of an even function, such as cosine, will be symmetric about the y-axis if we're graphing y equals cosine of x. If f is an odd function, such as sine, then the graph of, in this case, y equals sine of x will be symmetric about the origin. We still have those properties, and we're going to exploit them in the next section. So that was group number 4, the even, odd, or negative angle identities. For example, the cosine of negative pi over 6 and the cosine of pi over 6 are both root 3 over 2. That's an example of applying the identities. Sine of pi over 6 is 1/2, so sine of negative pi over 6 is negative 1/2 because sine is odd. Next, we're going to do our 5th group, the last basic group of identities. Going back up to here. Our 5th group will be the Pythagorean identities. These 3, and that's next time.
All right. Any questions so far? Cosine of, the cosine function and its reciprocal, the secant function, are even. The other 4 are odd. That's important with how to handle that negative sign you see. Questions? Questions? Pythagoreans up next. And also have some cute memes. Oh, where it should be in the notes. Yes. Oh, that's a good point. Now, these can be found at the beginning of 5.1. I know that's past the scope of chapter 4, but 5.1. Also, these are handouts on my website. Okay, that's a good point. They're summarized on my website and also the beginning of chapter 5. Right. Yeah, but thank you for reminding me. Yes. So, so this particular sheet, you may not find this particular sheet in chapter 4, but they're on my website, and they're in section 5.1, which summarizes this. But thank you very much. Yes. Any questions before we go to the Pythagoreans? Okay. Last but not least, actually, I'd say there's about third, maybe even second, maybe in importance. All right. And by the way, in case you haven't noticed, I did pump up the volume a little bit. Okay. All right. Shall we go on? All right.
Hi, everyone. We're going to cover our last group of basic trig identities, the Pythagorean identities. Last but not least. In fact, I'd say they're probably the third most important group. The most important group, I'd say, are the reciprocal identities, then quotient, then these guys, the Pythagoreans, then even odd. Those help in calculus, for example. And then cofunction, you'll see once in a while, but those are probably at the bottom. Those are probably the least. But the Pythagoreans, they're pretty important, and we'll deal with those right now. Know these three, or at the very least, memorize this basic Pythagorean identity and figure out the other two. All right, let's start by basically showing this first one and why it's true. The Pythagorean identities. All right, so let's consider the unit circle. Radius 1, that's the hypotenuse of this right triangle. Assume for now theta is acute. Okay, now remember that in order for Sohcahtoa to work, this side has to be sine of theta. In other quadrants, it could be negative as a sine length. This side here has to be cosine of theta. The x-coordinate of this point is cosine of theta. The y-coordinate of this intersection point is sine of theta. All right, look at this right triangle. The square of the hypotenuse equals the sum of the squares of the other two sides, the legs. The square of sine of theta plus the square of cosine of theta equals the square of 1. The square of sine of theta we denote as sine squared of theta. Move this up here. The square of cosine of theta is cosine squared of theta. The square of 1 is 1. So here's the basic Pythagorean identity. Sine squared theta plus cosine squared theta equals 1. It comes from the Pythagorean theorem. Now, even though it's hard to draw a right triangle for quadrantal angles, still, this holds for quadrantal angles, theta, and even for other quadrants. Symmetry helps. This is the basic Pythagorean identity. But there are two other identities in this category. Oh, but by the way, you can manipulate this as well. So, for example, we can also say that, for example, sine squared of theta is equal to, we can subtract cosine squared theta from both sides. This equals 1 minus cosine squared of theta. Sine squared of theta equals 1 minus cosine squared of theta. And similarly, cosine squared theta is 1 minus sine squared theta. Now, although those are different identities technically, still, if I ask you to write down the three Pythagorean identities, I think these are too closely related. If I ask for the three Pythagorean identities, I want this one, and I want the other two over here. Basically, I want one identity like this, one identity like that, one identity like that. So when you list the three Pythagorean identities, I want to see the squares of all 6 trig functions. But make sure that they're correct. They're easy to mess up. So how can we get from this first one to the other two? Well, one thing we can do is divide both sides by sine squared of theta. Don't worry about domain right now. We'll deal with that later. Let's take both sides, all terms on both sides, divide by sine squared theta. Sine squared theta over sine squared theta is 1. Plus cosine squared theta over sine squared theta is cotangent squared theta. That does work. 1 over sine squared theta is cosecant squared theta. So dividing both sides by sine squared theta, we get this second Pythagorean identity. And again, there are variations, but I'm not going to really call those different identities. They technically are, but I'm not going to really call those different identities. This is basically our second Pythagorean identity. Guess what? To get our third Pythagorean...
By the way, before I forget, this is the one advantage where the reciprocal of sine of theta is cosecant of theta, because notice the cos go together, right? That's a nice thing to remember. The cos go together in this identity.
Pythagorean identity. We're going to take this original Big Daddy Pythagorean identity and divide both sides, that is all these terms, by cosine squared of theta. Sine squared theta over cosine squared theta is tangent squared theta, plus cosine squared theta over cosine squared theta itself is 1, equals the reciprocal of cosine squared theta is secant squared theta. And here's our third Pythagorean identity. Tangent squared theta plus 1 equals secant squared theta. Okay, as it turns out, cosecant of theta and secant of theta are going to have the weirdest graphs. So you could think that the squares of the weird graph guys are all alone on one side. And the tangent or cotangent squared guys are together with the ones. It's easy to mess these up. When in doubt, derive these from the basic identity. So that takes us to our fifth and final group of basic Pythagorean identities. We'll have many more in chapter 5, actually, but we've done now our 5 groups of basic trig identities. Again, reciprocal first, quotient, and then in order, we did cofunction next as a third group, then even odd as our fourth group, and then Pythagorean as our fifth group. Although again, in terms of relating their importance, reciprocal identities tend to be the most common and most important, then quotient, then these Pythagorean identities, then even odd, then cofunction. That's my opinion. But know all these, love all of them, and be prepared to use all of them. All right, now finishing up the 4.2 to 4.4 block, we're going to save inverse trig functions for 4.7. I'll come back to this later when we cover 4.7, if you don't mind. And then word problems, if you don't mind, we'll postpone those till 4.8. So yay. I say for now we're done with the 4.2 to 4.4 block. We'll deal with these other issues later on. Thank you very much. Next up, how do you graph trig functions? Next time.
All right, actually, before that, I want to show you some really cute memes. Of course, I didn't create these. I'm not much of an artist. All right, Big Bang Theory fans. That's Wolowitz, right? This is a joke from MIT, so I don't know if you want to go to MIT now. I actually first heard this one from the show Beauty and the Geek. I wish I were sine squared and you were cosine squared so that together we could be one. You should really say sine squared x, whatever. Okay, that's Wolowitz. By the way, here are a couple more I forgot from last time. Pythagoras and Einstein fighting over c squared. I thought that was kind of cute. You can buy sweaters. This one. They should use meters or something, but you get the joke. All right. Anyway, so those are some memes I found. I didn't create these. I'm not sure if I'd be proud of ownership, but they're kind of corny, but kind of cute. I like them. All right, so back to business. Any questions? Any questions? All right.
Hi, everyone. Time to graph some trig functions, section 4.5. We'll start with graphs of sine and cosine functions. How do we graph y equals sine of theta? Now, I'm going to use theta instead of x because I still want to think of theta as an angle. All right. Also, I'm going to consider theta in radian measure, which corresponds to real numbers, which is more standard. Remember, in our classic picture of the unit circle, we associate sine of theta with the y-coordinate of this intersection point between this terminal side and the unit circle. So to graph one fundamental cycle for y equals sine of theta, we're going to take a tour from theta equals 0 to theta equals 2 pi and track the behavior of the y-coordinate. I do that in this copy of my notes. And I'm going to use what is called the frame method, which my colleague Tom Teagarden and which the author Carl Smith have used. So here's what we're going to do. I'm going to draw a Kit Kat bar where we have 3 horizontal line segments, evenly spaced, and 5 vertical line segments, evenly spaced, like this Kit Kat candy bar. The theta axis, or sometimes the x-axis, will go through the middle, this middle line segment, and the y-axis, which I'll label as f of theta, the y-axis will go through the left edge over here. The origin, for right now I'm calling that the pivot, it's the pivotal point on this frame. The origin is at the left center of the graph. All right, I claim that a fundamental cycle for y equals sine of theta will look like this. I call this a good morning graph because you have a hill on the left. It's like we have a happy morning, and we have a valley later on. Okay, it's like a low-key night. So a good morning graph. So why is this the fundamental cycle for y equals sine of theta? Again, we're tracing the behavior of the y-coordinate. I'll shrink this. We're tracing the behavior of the y-coordinate along the unit circle. All right, so starting here, theta equals 0. When the angle theta equals 0, this flat angle, here's the corresponding intersection point. The y-coordinate here is 0. When theta is 0, theta is like x here on this graph. When theta is 0, y, or the sine value, is 0. So when theta is 0, y is 0, 0, 0 is on the graph. The origin, the pivotal point, is on the graph, the red graph here. As we increase the angle from 0 to pi over 2 radians, and we travel through quadrant 1, what's happening to the y-coordinate, the sine value? The sine value, the y-coordinate, is increasing from 0 up to 1. And the sine of pi over 2 is 1. Remember, S-I-N, the sine of pi over 2 is 1. The sine value increases, and at pi over 2, the sine value is 1. By the way, notice that I'm writing the quadrantal angles on the bottom of this frame. 0, pi over 2, pi, 3 pi over 2, and 2 pi. I think it's nice to write these on the outside of the frame because I know that in trig, I always get annoyed when the graph runs into my coordinates, my numbers. So I like putting these numbers on the edges of the frame. And of course, that's fine. So again, the sine value goes from 0 up to 1. By the way, this part of the graph we're saying is concave down. Concave down. I'll shrink this a little bit. Concave down. meaning that the graph is curving downward. And that's the case between 0 and pi, as it turns out. Okay, this piece of graph here, from here to here, the graph is curving downward. The graph is concave down, kind of like square root did, right? That guy, concave down. And on graphs, you better get the concavity right. So we've gone from here up to here, which is a max point. We started at this middle pivotal point, and we're going up to this max point. It's one of the highest points on the graph. All right, now, as we go from theta equals pi over 2 to theta equals pi, what's happening to the y-coordinate or the sine value? We start at 1 here, and it's decreasing. Y or sine is decreasing towards 0, and sine of pi is 0. Over here, the sine value is decreasing. Sine of pi is 0. And again, we have a middle point here. It is also an intercept, a theta intercept. But in general, I might want to call this a middle point, or later an inflection point, because remember, we're going to move these graphs up and down later on. So it's not always going to be an intercept. Right now, though, for the fundamental cycle, y equals sine of theta, basic function, yes, this will be an intercept as well. All right, back here. The angle is changing from pi to 3 pi over 2. What's happening to the y-coordinate or sine value? It's going from y equals 0 down to y equals -1. The sine value is going down from 0 to -1. Sine of 3 pi over 2 is -1, and we're reaching a minimum point. This is one of the lowest points on the graph. And then finally, in quadrant 4, as theta goes from 3 pi over 2 up to 2 pi, the y-coordinate goes from -1 back up to 0. The sine value goes from -1 back up to 0. 2 pi is coterminal to 0, so it makes sense that sine of 2 pi equals sine of 0, which is 0. And we have completed a fundamental cycle for y equals sine of theta. The graph is concave down from theta equals 0 to pi. The graph is curving downward. However, the graph is concave up from pi to 2 pi. The graph is concave up over here. One thing that's convenient about the basic fundamental cycles for both sine and cosine is that the graph is concave down above this theta or x-axis. The graph is concave up below the theta or x-axis. That's true for cosine as well. All right, and notice here we have 5 key points on the graph, on these intersection points between these grid lines. We capture all these middle points. Right now they're intercepts. We capture this maximum point, and we capture this minimum point. Before, I referred to these middle points as inflection points, or IPs, which is kind of a calculus term. We mentioned these, remember, when we talked about logistic functions, where what we're hoping that coronavirus will do, where the graph is changing in curvature, right? So we have an IP here at these middle points, right? So an IP there, an IP over here at the middle point, an intercept right now, and an IP over here. And what is an inflection point? It's called an inflection point. You see this in calculus. What is an inflection point? It's a point where you have continuity, there are no breaks, and the concavity is changing. So here at this inflection point here at pi, the curve is going from concave down to concave up. That happens at all of these middle points. Right now, these are intercepts. All these intercepts here are also inflection points. In general, I'm going to call these points inflection points because, as I said, later on we're going to translate these graphs up and down, and they will no longer be intercepts, but they will still be inflection points. So this is an anatomy for the basic fundamental cycle for y equals sine of theta. Let's talk more about the features of this framing. Now, bear in mind, if you like your old method from Trig, Math 104, you don't have to use this framing that I'm doing here. However, you have to give me all the information that the framing method would have given me in a typical problem. Although you don't necessarily have to put in all these grid lines. I do think they're helpful, though. And as we'll see, it'll lead to some very nice, consistent, and systematic methods, which I think you might prefer to your Math 104 methods in Trig. So next, I will talk more about the framing. Okay. This is called 1 period. 2 pi is called 1 period, which we'll talk about later on. All right, but again, more about the frame, and then I'll talk more about the period and periodicity. Framing 1 cycle. Okay, so again, what were some key features? Drawing the cat bar. So if you're doing a sine or a cosine function, you do the 3 horizontal line segments and the 5 vertical line segments, breaking up this candy bar. And you're going to get 5 key points. For a sine or cosine graph, you're going to get 5 key points that are intersection points for grid lines. In this case, we're getting this point, the max point, this point, an IP, the midpoint, and the IP over here. We're going to always break these things up into fourths. For a cycle, we're always going to break up a cycle into fourths. Okay, so the period is 2 pi, and we're going to break it up into pi/2 increments. The left center point is this pivotal point. I'm going to call this point the pivot. It's the point that corresponds to the origin. Later on, it's the point that the origin will move to. And for sine and cosine graphs, the pivot will always be at the left center of the frame. For right now, it's at the origin. In fact, the pivot will be at the left center for all 6 trig functions, except for tangent. Tangent's going to be an exception. We're going to place the pivot at the center point for tangent. We'll see why. Again, it looks cleaner if we place coordinates on the bottom of the frame and to the left of the frame so that our graph isn't running into the numbers. That always used to annoy me as a student. Okay. Oh, and let's not forget, we need coordinate axes. It is not debatable that we need to label the axes. It's debatable what the order should be. So I might put the labels last. So theta here, y over here. I might put the labels last. But if you tend to forget, you might want to put these first. All right. But at some point, you have to label the axes. The theta axis is our horizontal axis. Later on, it will be x. The vertical axis is the y-axis. You must label the coordinate axes. A lot of people forget that. It's debatable whether you do it later or earlier. Usually you do it earlier, but later on, when we start to really transform these things, it may turn out to be better to label the axes at the end, not at the beginning. But make sure not to forget them. All right, so we framed 1 cycle for y equals sine of theta. Next, we're going to talk about the period being 2 pi, periodicity, the overall graph for y equals sine of theta, and we'll move on from there next time.
All right. Well, I had so much fun that I forgot to call a break. So it's 8:29. Break until 8:40. All right. So don't forget to mute. All right. And I'll come back and record. Back at 8:40. Seriously, I was having so much fun with this stuff, I forgot to call a break. And I know you were going, ah. Okay. But no, you're having fun too, I'm sure. I'll see you in 10 minutes, all right? Okay, any questions before we start? We'll wait about 20 seconds or so. Okay, any questions before we start? And we'll take questions after class today. Okay, let's proceed. Okay, we're up to part 7 now, all right?
Hi, everyone. We're continuing with our graph of y equals sine of theta, and we have the fundamental cycle over here, which we discussed earlier. In fact, we can actually graph this thing on Desmos, y equals sine of theta. By the way, in order to get these quadrantal angles here on the horizontal axis, you can go to the wrench here. I made the step size pi over 2 here, and you might want to resize the y-axis as well, the y scale. But I rescaled the x-axis, and I made the step size pi over 2 so that we have quadrantal angles as the labels here. When you start off Desmos, that usually is not the case. Also, I'm in projector mode, so you can see the coordinates better. Okay, now the fundamental cycle goes from 0 to 2 pi. Okay, annotate. The fundamental cycle goes from 0 to 2 pi. Oops. So this piece over here, this piece over here. All right. Now, here's a fundamental cycle. It's the good morning graph from theta equals 0 to theta equals 2 pi. The range, by the way, goes from -1 to 1. Those are all the y coordinates we pick up. Those are all the possible sine values we can pick up. Now, notice that if we keep zooming out, we see that this graph goes on and on and on. The domain is all real numbers. You can plug in any real value for theta, and you're good. Domain of this is all real numbers. So this fundamental cycle is repeated like a piece of wallpaper, forever and ever to the right and forever and ever to the left. Okay, so over here, here's our fundamental cycle over here, but then it keeps getting copied over here from 2 pi to 4 pi, from 4 pi to 6 pi, and so forth. Also back here, from -2 pi to 0. We have infinitely many cycles, and this graph is periodic. The function is periodic because we have this finite piece of wallpaper that gets repeated infinitely many times to the right and to the left, and that forms the entire graph. This changes in cycles. The period is 2 pi. That's the width of a fundamental cycle. The period here is 2 pi. Period equals 2 pi. The period is the width of such a cycle. A cycle is the smallest, thinnest piece of wallpaper that you need to have in order to have the property that when you repeat it forever to the right and to the left, you do get the overall graph. We need all of this cycle over here, but no more. This is enough for us to repeat. Over here, red cycle, blue cycle, purple cycle over here. We have 3 cycles over here, each of with 2 pi radians. And notice something else. This graph is symmetric about the origin. If you take this sine wave and you rotate it 180 degrees about the origin, you get the same graph. The sine function is odd. Sound familiar? The even-odd identities. The sine function is odd. The graph is symmetric about the origin. The graph is symmetric about the origin, which is the typical case with odd functions. So we have now the entire graph of y equals sine of theta. We have infinitely many cycles. This one over here, this good morning graph, is the fundamental cycle. Period is 2 pi. It's the width of a cycle, the thinnest piece of wallpaper that is sufficient. Okay, so that's the graph of y equals sine of theta. What about the graph of y equals cosine of theta? Cosine of theta corresponds to the x-coordinate of this intersection point. Let's trace it out. Again, I'm going to go to a frame. All right, so this is the fundamental cycle for y equals cosine of theta. Again, we have our candy bar, our Kit Kat bar here. 3 line segments here, 5 line segments vertically. All right, we're going from theta equals 0 to theta equals 2 pi. We're taking a tour around the unit circle here. And we're tracing the behavior now of the x-coordinate, the cosine value of theta. All right, when theta equals 0, The cosine value is the x-coordinate. What's the x-coordinate of this point? It is 1. Cosine of 0 is 1. When theta is 0, cosine is 1. We get a max point. Remember, I refer to the origin, or the point that corresponds to the origin, as the pivot, the pivotal point of the frame. For the basic sine cycle, the graph contained the pivot. But for the fundamental cosine cycle, that does not contain the pivot. It contains this maximum point up at 0, 1. Now, as we go from theta equals 0 to theta equals pi over 2, the x-coordinate, the cosine value, does what? It decreases from 1 down to 0. Cosine of pi over 2 is 0. Remember COS? COS, that trick. Cosine of pi over 2 is 0. The cosine function decreases in quadrant 1. Cosine at pi over 2 is 0. And we get this theta intercept. In general, I'm going to call this an inflection point, a point where the graph changes concavity, in this case from concave down to concave up. Because later on, when we translate this graph, this may no longer be an intercept. It's still an inflection point. All right, as we go from theta equals pi over 2 to theta equals pi, what's happening to the x-coordinate, the cosine value? It's going down from 0 to negative 1. Cosine value, cosine value goes from 0 down to negative 1. Cosine of pi is negative 1. The x-coordinate here is negative 1. All right, going from theta equals pi to theta equals 3 pi over 2 through quadrant 3, the x-coordinate, the cosine value, increases from negative 1 back to 0. So the y-coordinate here on this graph goes from negative 1 up to 0. Don't confuse coordinates here with coordinates there. Cosine values here correspond to y-coordinates here, not x-coordinates. All right. And then, as theta goes from 3 pi over 2 up to 2 pi, back to this east point, the x-coordinate, the cosine value, goes from 0 back up to 1. Over here, 0 back up to 1, a max point. So once again, just like for sine, we're picking up 5 key points. This time, we're picking up 2 maximum points, 2 inflection points. There's an inflection point over here, and 1 midpoint. I call this a valley graph, or maybe a curvy V graph. This is the fundamental cycle for y equals cosine of theta. Curvy V or valley. And don't forget to label the coordinate axes at the end. Theta over here at the right end. And remember, you put this at the positive end. Don't put theta over here. Put the label at the positive end. People forget that. And then we put y or f of theta up on top, not on the bottom. Remember, you put it at the positive end of each axis, the label. All right. Once again, the period is 2 pi. So here's one cycle in red from 0 to 2 pi, another cycle in blue, over here another cycle in purple. On Desmos, let's graph y equals cosine of theta. Okay, starting at 0, 1, here's a curvy V going to 2 pi, 1. That's a fundamental cycle. But then we repeat this. So we have 0 to 2 pi, 2 pi to 4 pi, 4 pi to 6 pi, also backwards. Negative 2 pi to 0, for example. We have infinitely many cycles. Periodicity. Period is still 2 pi. Again, 2 pi is the period because that's the width of a cycle. A cycle is the thinnest piece of wallpaper we need, with the property that when you repeat it forever, left and right, we get the whole graph. All right. Oh, and let's notice something else. We have symmetry. What kind of symmetry do we have? We have symmetry about the y-axis. And why is that? Because cosine is what kind of function? It is even. Cosine is an even function. Cosine is even. We have symmetry about the vertical axis, the y-axis. And let's notice something else. Here's y equals cosine of theta. This was y equals sine of theta. You know what? It's the same shape. the sine wave and the cosine wave is the same wave, but they're horizontal translations of one another. That's not so surprising because we're basically tracking the behavior of the x and the y coordinates around this unit circle. It's not so surprising that it's the same basic kind of behavior, but there's like a phase shift, right? Okay. So that's the graph for y equals cosine of theta. It's a horizontal translation for the sine graph. Okay. Now, next time, we're going to talk about domain, range, amplitude, period, translations, various transformations. Next time.
But first, let's have some fun, okay? Time for some fun.
Hi, everyone. Let's first talk about domain and range for sine and cosine, the basic sine and cosine functions. All right, y equals sine of theta. All right, let's take a look. Domain. What are the x coordinates we pick up? We pick up all real numbers as x coordinates. Domain is all real numbers. What about the range? The y coordinates we pick up? Only the real numbers between -1 and 1. Even if we zoom out, we're just wobbling between -1 and +1. All right. Same for y equals cosine of theta. That's just a horizontal translation of the sine graph. Same domain, all reals, same range, still from -1 to 1. So if f of theta is sine of theta or cosine of theta, the domain of f is all reals, we never have a problem. The range of f is the closed interval from -1 to 1, which makes sense because we're talking about sine values and cosine values. We're talking about, on the unit circle, the possible y coordinates and x coordinates we get along the unit circle as we travel all around the unit circle. So we pick up all of the real numbers between -1 and 1 for both y, or sine of theta, and x, or cosine of theta. All angles work out. We never, sine and cosine never have a problem for any angle. Domain is all reals. All right. Now what happens if we put a number in front of sine of theta or cosine of theta? In general, how do you graph f of theta or y equals a sine of theta or a cosine of theta? What could happen? Let's ask Desmos. Here's y equals sine of theta. What is the graph of y equals 2 sine of theta? Remember chapter 1. What happens if you multiply the right side by 2? Y equals twice sine of theta. You double all the y coordinates. That leads to a vertical stretch. From the green graph to the black graph, it's a vertical stretch by a factor of 2. What about y equals 3 sine of theta? That's the red graph. We're stretching by a factor of 3, and so forth. So if you're multiplying sine of theta by a number greater than 1, you're getting a vertical stretch. But let's say we multiply by 1/2. What happens if we multiply by 1/2? Y equals 1/2, or 0.5 times sine of theta. We're going from the green graph to the blue graph. That's a vertical shrink. We're squeezing the graph towards the x-axis, or the theta axis in this case. Y equals 1/3 of sine of theta. It's like almost gravity almost. That dark green, thick green graph, that's very squeezed towards the theta axis. What if a is negative? How do you graph y equals the opposite of sine of theta? What happens when you multiply the right side by -1? Remember section 1.4. Y equals the opposite of sine of theta. That's the purple graph, upside down. Again, the green graph here becomes the purple graph over there. The graph is flipped. It's reflected about the theta axis, which was the x-axis. Reflection about the horizontal axis. y equals negative 2 sine of theta, two things happen. Okay, as we go from the green graph to the black graph, we get a flip, a reflection, and also a stretch. So what can A do? A can lead to a vertical stretch or shrink, and if A is negative, it leads to a flip, a reflection about the horizontal axis. Again, if A is positive, and if A is greater than 1, it's a vertical stretch. If A is like 1/2, strictly between 0 and 1, it's a vertical squeeze. If A is negative, you reflect about the x or theta axis. Okay. Now, with our general frame method, here's the deal. We're going to ask if we have a sine function or a cosine function, and we're going to ask if A is positive or negative. If A is 0, you're destroying it, right? That's not a trig function. All right, so if A is positive, we have our classic shapes, our classic cycle shapes. A good morning graph for sine, a valley or a curvy V for cosine. And then if A is negative, we flip or reflect about the horizontal axis, this middle line. So instead of good morning, we have good evening for sine. Instead of a valley, we have a hill, kind of a pimple up there for cosine. We flip, we turn it upside down. These are the cycle shapes. So if we're going to graph one cycle for a transformed sine or cosine function of the type I could give you, then you're either going to graph a good morning shape, a good evening shape, a valley shape, or a hill shape. Now granted, consider the graph of y equals sine of theta. It's true that all four of these shapes are achieved and attained eventually on that curve, but we're going to describe a method where you're going to use one of these four particular shapes in order to graph one cycle using our frame method with appropriate coordinates. So remember these four shapes. Okay. A determines the amplitude for the function or the graph. So if we graph y equals a sine of x or y equals a cosine of x, I'm going back to x now, all right? The absolute value of A is the amplitude of the graph. It's half the height of the graph. So for example, here's the graph of y equals cosine of x. The amplitude is 1 because the coefficient, well, it's kind of a coefficient. A equals 1. A equals 1 here. Okay, the total height of the graph, the total height of the graph is 2. Half the height of the graph is 1, and that's the amplitude for the function or the graph. The range is going from -1 to 1. What about y equals 2 cosine of x? Okay, so here's y equals cosine of x first in green. Here's y equals 2 cosine of x. What happens? Vertical stretch. We go from the green graph to the red graph. What happens? The amplitude is doubled. The amplitude goes from 1 to 2, and the range, by the way, is now -2 to 2. It's also stretched by a factor of 2. So for y equals 2 cosine of x, the amplitude is 2, half the height of the graph. The total height is 4, half the height, the amplitude, is 2. Y equals 1/2 cosine of x, that's a vertical squeeze. The amplitude is 1/2, it's small. For y equals -2 cosine of x, we're taking this v guy and turning him upside down, all right? Well, this guy's upside down, but these two equations here, y equals 2 cosine of x and y equals -2 cosine of x, the amplitude is the same. It's 2 in both cases. The absolute value of -2 is +2. Amplitude, by definition, is always positive. Okay, amplitude is the absolute value of A, and it's half the height of the graph, half the height of the graph. So we've described the impact of A, this number in front of sine of x or cosine of x. It can lead to a vertical stretching or shrinking, and if A is negative, it leads to a flip. Next, we're going to consider what happens if we put a number in front of the x. That's next time.
Any questions so far? Okay. We've described the impact of A, which is like a coefficient. Questions so far? All right, you can put questions in chat. Let's proceed.
Hi, everyone. We're continuing with graphing sine and cosine functions. Before, we talked about the impact of putting a number in front of sine or cosine. That led to vertical stretching or shrinking, maybe a flip. Now we're going to talk about what happens if we put a number in front of x. We're substituting. These are substitutions. We're substituting x with bx. How do we graph y equals a sine or cosine of bx? Again, these involve substitutions. Okay. Subbing x to bx. Okay. Well, let's experiment. Here's y equals sine of x, classic sine wave. What happens with y equals sine of 2x? Okay. What happens when we put a 2 in front? Going from blue to green, it's a horizontal squeeze. Now again, from chapter 1.4, remember that the horizontal transformations were confusing, right? For example, normally if you stick in a 2 in front, that's a vertical stretch. But if you substitute x with 2x, that's not a horizontal stretch, it's a horizontal squeeze. Remember, when you substitute, you get a surprise. When you substitute, you get a surprise. When you substitute x with 2x, you don't get a horizontal stretch, you get a horizontal squeeze. Okay, what about y equals sine of 5x? That's even more hyper. Okay, that's even more squeezed in purple. The period shrinks. Notice that as p increases, the period shrinks. We can think of b as an aging factor. In fact, look at it this way. Here's a graph of y equals sine of x. By the way, my former professor, Peter Doyle, came up with the idea of b being an aging factor. If b is 2, look at this. Before, we had one cycle in blue between 0 and 2 pi. Now in green, we have 2 cycles. 1, 2. B here, the 2 here, tells you the number of cycles on the new graph that fits into the old period, 2 pi. On the blue graph, you had 1 cycle between 0 and 2 pi. On the green graph, you have 2 cycles between 0 and 2 pi. That means the period, by the way, is half that, or pi, right? From here to here, it's pi. Accordion effects. It's kind of like we're squeezing and stretching an accordion here.
Or spring.
Instrument. Let's assume b is positive. We're assuming for now b is positive. If b is greater than 1, surprise, it's not a horizontal stretch, it's a horizontal squeeze, right? Here b is 2, we get a horizontal squeeze from blue to green. If b is between 0 and 1, like 1/2, we get a horizontal stretch. I'll show you. So instead of y equals sine of x, we have y equals sine of 1/2 x. Okay, we're going from blue to green. The thick green graph, that's stretched out. So we have only half of a cycle between 0 and 2 pi. The full period is 4 pi from here out to here. The period is doubled. Okay, and that's a horizontal stretch. So the period of y equals a sine of x or cosine of x is 2 pi. Remember, a had no impact on the period. A affects amplitude and the flipping aspect. A had no impact on the period. It was 2 pi for these. But b can have an impact on the period. In general, the period, which is the width of a cycle, the width of a piece of wallpaper, the period for these guys is in general 2 pi over b. We're assuming b is positive. If b is negative, or if b could be negative, then to be safe, put absolute value. But if we know b is positive, then the period is given by 2 pi over b. As b increases, the period shrinks. As b increases, the period shrinks, and we get a squeeze. Again, we can think of b as an aging factor. The higher b is, the more cycles we can fit in where we just had 1 cycle before. So again, if we have y equals sine of 2x, we have 2 cycles, where there used to be just 1. Y equals sine of 3x, we have 3 cycles, where we used to have just 1 on blue. What if b is negative? Then that's kind of weird. Then the idea is that we kind of graph backwards, and we want to avoid that. So if b is negative, let's go ahead and apply the even-odd properties. Because if b is negative, you're in a bad place, and you're going to want to fix that immediately so that the new value of b is positive. We want b to be positive when we start analyzing. All right, so for example, let's graph a few cycles of y equals -7 sine of -3x. Big problem, the negative sign there. B is negative. It's -3. We hate the fact that b is negative. So we're going to apply the even-odd properties. We do not want to graph backwards. It's like a time reversal. Well, is sine even or odd? Is sine even or odd? Sine is odd, which means that this negative sign basically pops out. Okay, so sine of -3x is the opposite of sine of 3x. -7 times -1 sine of 3x is +7 sine of 3x. Informally, the way you can look at this, because sine is an odd function, sine is odd, and -3 is a factor on the x, this negative sign pops out and changes the negative to a positive. So both of these basically knock out. The negative sign pops out, changes the negative to a positive. We don't have any more negative signs. So here we have an easier problem. Instead of graphing y equals this, let's graph y equals 7 sine of 3x, and that's okay because these are equivalent equations. They have the same graph. Graphing this is just as good as graphing that. It's the same graph. And how do we graph this? A equals 7, amplitude is 7, there's no flipping, A is positive. B equals 3, so we're squeezing in horizontally. We have 3 cycles now where there used to be 1. The amplitude is 7, the period is 2 pi over b. B is 3 now. We take the new value of b. The period is 2 pi over 3. So we have this. The graph goes from -7 to 7. The amplitude, the half height is 7. The period is 2 pi over 3. So from 0 to 2 pi over 3, as far as x goes, that gets 1 cycle. We have another cycle from 2 pi over 3 to 4 pi over 3, and a third cycle in blue from 4 pi over 3 to 2 pi. The purple cycle, the red cycle, the blue cycle, we can fit 3 cycles now where we used to have 1, if b were just 1 over here. We have 3 cycles between 0 and 2 pi. Right. Desmos confirms that. Here's y equals 7, that stretches vertically by a factor of 7. Oops. Y equals 7 of 3x. Wow, very hyper. I'll zoom in. By the way, one way to verify equivalence, graph the original. We're just going to recolor the graph. This is the same graph. Y equals -7 sine of -3x. We're just recoloring the graph. It's the same graph. Equivalent equations, same graph. All right. So once again, as we change b, we change the period. Y equals 7 sine of x, period is 2 pi, like before. What about y equals 7 sine of 1/3 x, or x over 3? When in doubt, write x over 3 as 1/3 x. B here is what? B here is 1/3. That leads to a stretch. We're stretching. Okay, it's stretched out by a factor of 3. The period, 2 pi over b is 1/3. If you divide by 1/3, you're multiplying by the reciprocal, 3. 2 pi times 3 is 6 pi. It's stretched out. So again, going from y equals 7 sine of 3x, y equals 7 sine of x, not as hyper, y equals 7 sine of 1/3 x, more spread out. Next up, we're going to frame one cycle and be detailed with the key points and coordinates, and then translations. Next.
Now, if you're really good at your trig class 104, of course you can use your old methods, but give me all the information my method would give you. But you know, if you felt your trig book wasn't very good, then this method may offer you a more structured way of looking at things. I think many students find this to be an improvement. I think it's probably better than most books. But again, feel free to use whatever method you want, but give me the information that I would have wanted, and you know, show me appropriate work, right? What's the period and so forth. Okay, frame method.
Hi everyone, here we go. A frame method for graphing trig functions. I think some of you could really like this as a superior alternative to what you did in Math 104. But if you like your old school way of doing it from your trig class, that's fine. Just make sure you give me all the information that this method would give me on a standard problem. All right. Now, the mnemonic or memory device is Pikapi. Actually, I'm going to add an A at the end, Pikapia. I kind of made this up, but it's easy to remember, Pikapia. Frame method is basically Pikapia. To graph y equals a sine or cosine of bx, and will extend to other trig functions later on. Pikapia, Pikapia. P, first P for pivot. The left center point on the frame is the origin for now. Later on, it might be translated elsewhere. C for cycle shape. That's from this grid over here, remember? First A for amplitude is the absolute value of A, half the height of the graph. Second P for period, 2 pi over B. Remember, if B is negative, use the even odd identities to make sure the new B is positive. I for increment, which is always 1/4 of the period. This will help us graph. It's the step between our key points on our graph. And finally, A, the Pikapia, A. Last A, we will superimpose the coordinate axes, perhaps not to scale. Okay, so put in the coordinate axes and label them. We usually do this first, but you know what? Especially when we translate, we might want to do it last. Pikapia, don't forget the axes and to label them. Let's apply this idea. Example, use the frame method, or not, you can use your method, but give me all the information we'll see here. Use the frame method to graph one cycle of the graph of y equals -3 cosine of -4x. There are infinitely many possible cycles or answers, but the frame method will suggest a particular cycle. Okay, big problem. B is what? B is -4, which is negative, and we don't like that. So we're going to use the fact that cosine is what? Even or odd? Cosine is even. So what can we do with the negative sign here? This -1 is a factor on the argument. We can kill it. Because cosine is even, so that means that the negative sign here, we can delete. This is equivalent. Y equals -3 cosine of 4x. I'd rather graph that. We're going to get the same graph. It helps that -1 is a factor here. If you had a loose term in there, like a plus pi or something, then you'd have to factor out the -1 first. All right. The pivot is at the origin, 0, 0. We're not translating yet. Cycle shape. Okay, B is positive. I'm assuming B is positive, by the way, when we do this. We have cosine and A is negative. You should have the cycle grid in mind. Cosine, if A is positive, we have the valley, but if A is negative, we flip over to this hill or pimple. we want this over here, the hill, if we're going to apply the frame method. Amplitude, the absolute value of A, the absolute value of -3 is +3. The period is 2 pi over B. What's B? Okay, well, let's look at the new value of B. The new value of B is 4. The new value of B is 4. Positive. 2 pi over 4 simplifies to pi over 2. The increment is always 1/4 of the period. 1/4 times pi over 2, multiply across, is pi over 8. It's going to be the distance between each of these vertical grid lines. And then don't forget to put in and label the axes at the end. All right. We have enough information to do our full-blown example. We're going to do the full-blown graph. And actually, I'm going to go ahead and duplicate my file here. All right. And we're going to see what we get. All right, here we go. The answer is here. Let's explain why. Okay, the Capia, how does it give us the answer? The pivot, left center, 0, 0. Notice 0 here, 0 over here. Cycle shape, we have the hill. And we're going to get 5 key points, remember. 5 key points. This min point, this inflection point, this max point, this inflection point, this min point. Amplitude is 3. 0 plus 3 is 3. 0 minus 3 is -3. By the way, the range will be from -3 to 3. Period, pi over 2. Well, if this is 0, the period is over here, pi over 2. It's the width of the frame. Increment, pi over 8. That's the number we're going to keep adding. 0 plus pi over 8 is pi over 8. Pi over 8 plus pi over 8 is 2 pi over 8. That simplifies to pi over 4. 2 pi over 8 plus pi over 8 is 3 pi over 8. 3 pi over 8 plus pi over 8 is 4 pi over 8. That's a check. That simplifies to pi over 2, the period. By the way, if this is 0, then this here is the period. Bear in mind, if this is not 0, then this will not be the period. But since we're not translating yet, the period is here, pi over 2. Finally, the axes. The equation of the x-axis is y equals 0. Well, here's 0. Label it x on the right end, the positive end, not the left. The y-axis is at x equals 0. Here's 0. It's at the left edge. Put the y here on top, not the bottom. We put the labels on the positive directions. And there we go. That's a completely labeled cycle for the graph. All right. What about translations? By the way, if you need a second cycle, you can go on the other side of the y-axis and subtract or use symmetry. Translations. This should sound familiar. All right. So what if we wanted to do a translation so that the origin 0, 0 becomes the point, not HK, PD. This is standard notation for trig, P comma D, where P is the horizontal or phase shift. I'll type that out. P is the horizontal or phase shift. And D is, as usual, the vertical shift. Well, it's usual for trig. Okay. Remember what we do. If we do a horizontal translation, we substitute x with x minus p. We substitute the x here, or here, with x minus p. Substitute with x minus p to do a horizontal shift by p units. To do a vertical shift of d units, just attach a plus d. So it's easy to read off a vertical shift. So these are our general transformed sine and cosine equations. And they lead to transformed graphs. Okay. So how do we use the frame method in the case of translations? Fortunately, it turns out this is just a translation of the guy we just did in the previous example. Use the frame method, or use your method, to graph one cycle of y equals -3 cosine of 4x plus pi, all plus 2. Again, much of Picapia will be the same, but there will be some differences. All right, so for example, how do we find the phase shift? One method is to factor b out of the argument. Right now the argument is 4x plus pi, b is 4. Factor out the 4. You get x plus, when you factor you divide, we get pi over 4 here. Okay, and what is x plus pi over 4? It's x minus negative pi over 4. So p is the phase shift. Remember, in this general format, p is the phase shift. So over here, p is negative pi over 4. It's what makes this equal to 0. What is the value that makes this equal to 0? Negative pi over 4. All right. So the phase shift is negative pi over 4. D, we just pick up here, the plus 2. So the pivot, P comma D, is at -4, 2.
Negative pi over 4.
That's where the origin is moved to. It's at the left center of our frame. Now, if you thought the factoring method was a bit too confusing, as long as B is positive, if B is negative, you really need to factor something, at least a -1 out. But if B is positive, well, there's an easier way to do things. You just go ahead and set this argument, 4x plus pi equal to 0, and solve for x. 4x plus pi equals 0. To solve for x, you subtract pi, divide by 4. X is, hey, negative pi over 4. That's the same phase shift that we got before. Okay. So that is the key difference. Everything else is the same. Cycle shape is a hill. Amplitude is 3. Period is pi over 2. Increment is pi over 8. Remember, this guy was a transformed version of our previous example and put in the axis. So the pivot, that's the new thing here. And what is our new answer, our new graph? The coordinates and axes will be the things that really change. All right, the same picture, it's a hill. What's different? The pivot is at the left center of the graph. The pivot is at -4.
Negative pi over 4. I had a note to myself. I made that mistake twice. Sorry. Negative pi over 4.
Comma 2. The left center of the graph, where the origin is moved to, is at the left center. It actually is not a point on this graph, this cosine graph. All right. Cycle shape, it's a hill. We can draw on this hill with the 5 key points here. Amplitude is 3. We have to do some arithmetic. 2 plus 3 is 5. That's the y coordinate of this max point. 2 minus 3 is -1. That's the y coordinate of these min points. You must write down these numbers. The period is pi over 2, but this here is not pi over 2 because the left number here is not 0. So in a way, we do not use the period directly. We use the increment directly. Okay, the increment is pi over 8. Ooh, well, this is in fourths, so let's convert to eighths. negative 1/4 pi is negative 2/8 pi. 1/4 is 2/8, right? So negative 1/4 pi is negative 2/8 pi. Negative 2 pi over 8 plus 1 pi over 8 is negative 1 pi over 8. That's simplified. Negative 1 pi over 8 plus pi over 8 is 0. Wonderful. We can keep adding pi over 8, or we could just use symmetry. Pi over 8, symmetry about 0. This is pi over 8. This is pi over 4. Where does the period come in? The period is pi over 2. Where does the period come in? Pi over 4 minus negative pi over 4 is pi over 2, the period. The period is the width of this cycle. Pi over 4 minus negative pi over 4. That's the period. All right. A for axes, remember, that was the missing piece here. Picapia. You got to put in the coordinate axes. Got to put in the coordinate axes. All right. The x-axis is at y equals 0. Okay, now 0 is between negative 1 and 2. I'm not going to get out a ruler, but make sure that the x-axis is between this line over here and this line over here. 0 is between negative 1 and 2, okay? And then label the x on the right end. The y-axis has equation x equals 0. It's right here. Put the y up on top.
So I don't know what happened here. Is this it? Oh, no.
Sorry about that. Put the y up on top.
Blooper. All right, sorry.
All right. That's a cycle for a transformed trig function. All right. So after today, we're going to look at the other 4 trig functions. Until then.
So it's pretty much done anyway. Okay. All right. So we're at 9:30. I'm on time. Okay. We'll deal with tangent and others next time. It's been a good day, but I will stick around for questions as promised. Okay. So we're done through 4 or 5. If you're following lectures, you can do all the homework through 4.5. I'm grading. Okay. So I'm hoping to have, I think I might start with chapter 1. I'll see, but I should have results by the end of the week. Maybe Saturday. Questions? Thank you very much. Thank you. Yes, great interaction today. I will stick around for questions, by the way. I will stick around for questions. Okay, so you can either unmute or if you want to ask me questions in chat, that's fine. I will stick around. And I will keep recording unless you tell me to pause or stop the recording. I will keep the recording. The students appreciate these homework sessions. Okay, any questions? Any questions? Take care, yes. Okay, so why don't we do this? I'll be back at 9:37, and if there are any questions by then, let me know. So I will return at 9:37. Okay, so I'm letting you gather your thoughts. Otherwise, have a good night. But let's pause till then.